So let me give you 4 important formulas, okay? So 4 important let's call this, I don't like formulas, but let's call this formulas. Okay, so always involving sums. So the first one is the sum when I goes from 1 until n of 1. Okay, so this is pretty straightforward. So I'm adding 1 n times. Okay, so basically this is when I is 1, it's 1. Plus when I is 2, it's still 1. Plus when I is 3, it's still 1. Plus, 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 all the way I stop at n. Okay, so if I sum from 1 to n, 1, I'm getting just, of course, n. Right? It's 1 plus 1 plus 1 n times. Okay, so this is straightforward. Second, sum I equals 1 until n of I. Okay, so now when I is 1, it's 1. Plus when I is 2, so it's 2. Plus when I is 3, well, that's 3. And so on until my last term, which is n. Okay, so basically if I sum from 1 to n, there's a way to find the formula here. And this formula, does anybody know it? Okay, so it's n times n plus 1 divided by 2. That's how you find the sum of the first n terms. Okay, so there's a story that says that Gauss, he's a mathematician, he invented this when he was in elementary school. They gave him a punishment to add from 1 to 100, and so he just did it in 2 seconds and he invented this formula. Whatever, that's what they say. Okay, so let's do an example just for you to see and feel how this works. So for example, let's say the sum I equals 1 until 5 of I. Okay, well, this is 1 plus 2 plus 3 plus 4 plus 5. And if you calculate this, you get, so 3, 6, 10, 15. Okay, and if we do it using the formula, well, n is 5, so n times n plus 1, so 5 plus 1 over 2, and you get 5 times 6 is 30, 30 over 2 is 15. Okay, so as you see, this works. Okay, any questions so far? Okay, so it's important to know that the sum of the first n integers, or n natural numbers, the first n natural numbers, is n times n plus 1 over 2. Let's do another one. Sum I equals 1 until n, now of I squared. Okay, so this will be, of course, 1 squared plus 2 squared plus 3 squared, and so on until n squared. Okay, the formula for this is n times n plus 1 times 2n plus 1, and all this divided by 6. Okay, so these ones you have to know by heart. Okay, so the first one is straightforward. The second one is easy to remember. The third one is a bit tricky to remember, but you'll see. We'll do examples. We're going to use this, and it's going to register. Okay, next one. So let's do an example for this one. So let's do the sum. I goes from 1, let's say, to 3 of I squared. So that's 1 squared plus 2 squared plus 3 squared, right? We stop at 3. Let's calculate this. So it's 1 plus 4 is 5, and 5 and 9 is 14. And if I use a formula, so I will get 3 times 3 plus 1 times 2 times 3 plus 1, and all this over 6. And what do I get? 6 times 6 plus 1 is 7. 7 times 4 is 28. 28 times 3 is 84. And 84 over 6 is 14. So again, this formula seems to work. Of course, that's not a proof. Okay. A proof would be to check that it works for every n. I just checked for n equals 3 here, and it worked. I checked for n equals 5 here, and it works. I mean, it's a hint that it should work, but that's not a proof. Okay, so we're going to prove it. Okay, and the last formula is this one. Sum I equals 1 until n of I cubed. So 1 cubed plus 2 cubed plus 3 cubed and so on until n cubed. Okay, and the formula for this one is pretty easy. It's exactly the same as this one here, but squared. So it will be n2 n plus 1 squared over 4. Okay, let's do an example for this. Sum I equals 1 until 3 of I cubed will be 1 cubed plus 2 cubed plus 3 cubed, and that is equal to 27 and 8 is 35 and 1 is 36.
Sir, is it like 2 power, no, n power 2 times n, and what's after that?
N plus 1 here.
Okay.
You can't read, so I'm going to fix it. This is n plus 1. Let's use the formula here. So n squared, so 3 squared, times n plus 1, so 3 plus 1 squared over 4. So I get 9 times 16 divided by 4. I'm going to get exactly 36 again. So again, this works. You checked. Again, that's not a proof, but at least we did a spot check and it worked. So here's the main idea. So to prove a, let's say, statement induction. First, verify that the statement is true for n equals 1. And second, and that's going to be the induction step, assuming that it is true for n, prove that it is true for n plus 1. So this is the process of proving a statement by induction. Okay, so usually we prove by inductions statements that we want to show that they work for all values of n. Okay, so I'm going to do an example now to prove the first one, and you will see how you're going to understand this. Okay, so for example, show that the sum I equals 1 until n of 1 is equal to n. Okay, so this is obvious, right? It's 1 plus 1 plus 1 plus 1 equals n. We know that. But let's prove this, that this works for all n. Okay, so this I have to say for all n in n. So for all integers, for all natural numbers. Okay, so step 1. We verify, I'm going to write a bit of English here. We verify that it works for n equals 1. Okay, let's do this. So when n equals 1, what happens? So the sum I equals 1 until 1, right? N is 1, of 1. So this is just 1. And if I use the formula, that's going to be the n, which is 1. It works. Okay, if you try to get your answer using the left side or the right side using n is 1, you will get the same thing. You understand this? Okay. The second one, the second part of the induction proof. So we assume that it works for n. Okay, in other words, we assume this. Sum I equals 1 until n of 1 is equal to n. We assume that this is true. We want to show that it's works for n plus 1. In other words, that the sum I equals 1 until n plus 1 of 1 will give me n plus 1. That's what I want to show. Just assuming this. Do you understand? Okay. So let's go. Let's see this. Sum I equals 1 until n plus 1 of 1. This is what? Well, this is 1 plus 1 plus 1 plus 1 plus 1, n plus 1 times. This is equals to sum I equals 1 until n of 1, because there's just n of them, and then plus 1. But we assumed that this sum is n. So this is n plus 1, and that's it, it's proven. Proof is done. So, example, show that the sum of the first n natural numbers is n times n plus 1 over 2. Okay, so let's do it. First thing, as usual, we verify that it works for n. For 1, sorry, for n equals 1. Let's try with 1. So sum I equals 1 until 1 of I. So that's equal to just 1. And it's equal, if I plug in 1 here, I get 1 times 1 plus 1 over 2. And that's good. Okay, you understand this sentence here? Okay, I plug in 1 in the n. So from 1 to 1 of 1 is of I is just 1. If you plug in the 1 on the right side, you get 1 times 1 plus 1 over 2. It's still 1. That works. Second, so assuming that this is true, so sum I equals 1 until n of I is equal to n times n plus 1 over 2. Okay, we want to show that. Now, can you tell me what do we want to show here? That it holds for n plus 1, which means that the sum I equals 1 until n plus 1 of I will be what? Can you tell me?
n plus 1 times n.
Go. N plus 1 times?
N plus 2 over 2.
Very nice. Okay. Who doesn't understand what he just said here? This is very good. Okay, so just assuming, it's weird because we're using what we're trying to prove it. That's what seems weird, okay? But I'm going to explain you the logic behind it after. Okay, so we're assuming that this is true, and you want to show that if instead of having an n here, I had an n plus 1, it would still work. In other words, this n will also be replaced by n plus 1 in the answer. Questions?
So for each n, you would replace it by 1, like n plus 1.
Exactly. Okay, so let's do it. I'm going to start with the left side here and develop it, right? Open it up and hope to get to this. And I'm allowed to have a little trick up my sleeve. I could use this. Okay, so I equals 1 until n plus 1 of I. This is what? Well, this is 1 plus 2 plus 3 plus all the way until n, and then plus n plus 1, right? That's what it means. Okay, I'm adding 1, 2, 3, 4, 5, 6, and n plus 1. Any questions? Okay. Now this sum from 1 to n, well, this is sum I equals 1 until n of I. This is this.
Sir, do you mind explaining that again for the n plus 1?
This here, this step
Yeah.
here? Sure. So if I'm going from I to n plus 1, it means I'm going 1 plus 2 plus 3 plus 4 plus 5 all the way until n plus 1. Is that okay?
Yeah.
Okay, I just wrote the term before. The term before n plus 1 is n. I just wrote it as well. You understand or no?
Yeah, I understand.
That's it. I'm going, so it's from 1. The term before that, I could write it also. It's n minus 1. I could write n minus 1 here also, but I don't need. This is just to show you that the first n terms of this sum is exactly the sum that we have up here. Okay, so let me continue here. So the sum I equals 1 until n plus 1 of I is equal to, well, apparently is the sum I equals 1 until n of I plus the last term, which is n plus 1. Are you okay with this? Okay, and now I'm going to use my induction assumption, which is that the sum from 1 to n of I is n times n plus 1 over 2. So I'm assuming that this is n times n plus 1 over 2. So this is equal to n times n plus 1 over 2 plus this one, which is n plus 1. Is there any questions until here? Okay, now I'm just going to do some algebra by finding the common denominator here. So I'll get n times n plus 1 plus 2 times n plus 1, all this over 2. Then I'm going to factor out an n plus 1 on top. I'm left with n plus 2 over 2. Oh, guess what? I found it. There you go. It works for n plus 1. I got what I wanted to prove. The proof is done. Okay, try this one. So show that sum I equals 1 until n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. Okay, so first thing, so for n equals 1, what happens? Sum I equals 1 until 1 of I squared. This is 1 squared, which is 1. And if I plug in 1 on the right side, I get 1 times 1 plus 1 times 2 times 1 plus 1 over 6. And if you check, you're going to get 1 as well. It works. Second step. So assuming that this is true, sum I equals 1 until n of I2 is n times n plus 1 times 2n plus 1 over 6. So we want to show that. What do we want to show? Can you tell me?
It works for n plus 1.
So sum, exactly. So sum, what does it mean explicitly? So sum I equals 1 until n plus 1 of I2 is what? So I replace every n here by n plus 1. So it's n plus 1 times n plus 1 plus 1, so n plus 2 times 2 times n plus 1 plus 1, which is 2n plus 3 over 6. That's what I want to show. Okay, so I'm going to put a question mark here. That's what I'm looking for. Okay, any questions until this step? Okay, so let's start. Yeah?
Do we like always replace n by n plus 1,
Yeah, always.
even though like it's squared, like I squared, whatever, doesn't change?
No, this has nothing to do. You'll replace the n by n plus 1 in the expression that you're trying to show.
Okay, perfect.
Okay, so now let's start now with the left side. So sum I equals 1 until n plus 1 of I squared. Okay, so again, I'm going to expand everything. So it's 1 squared plus 2 squared plus 3 squared plus and so on until the last term, which is n plus 1 squared. Okay, and the term before that was, of course, n squared.
Sir, I have a question.
Yes?
Where did you get the 2n plus 3?
The 2n plus 3 here comes from replacing n plus 1 in here. In here. You see? So 2 times n plus 1 plus 1. It becomes 2n plus 2 plus 1. It's okay?
Yeah.
Okay, now here, this is equal to the sum I equals 1 until n of I2, right? I'm going until n. So I'll continue up here now. Therefore, sum I equals 1 until n plus 1 of I squared is equal to the sum I equals 1 until n of I squared, right here, plus this term, which is n plus 1 squared. That's what I have. Okay, and now I'm going to assume, I'm going to use my assumption. So that means that it's equal to, so we said the sum from 1 to n of I squared is n times n plus 1 times, sorry, 2n plus 1 over over 6 plus n plus 1 squared. And so now I'm going to simplify this expression and hope to get to what I'm looking for. So it's n plus 1, 2n plus 1 plus, and now I'm going to 6 times this. So 6 times n plus 1 squared over 6. I can extract an n plus 1 here. Okay, so n plus 1 times, so here I will have n times 2n plus 1 plus 6 times n plus 1. I'm just doing some algebra here. Over 6, and that is n plus 1 times, and if I expand here, I will get 2n2 plus 7n plus 6 over 6, and this could be factored. N plus 1, n plus 2, and 2n plus 3. Over 6. And that's proven, done. Okay, we got the expression that we're looking to get.
Good.
Okay, so let's prove the last formula. So show that sum I equals 1 until n of I cubed is n squared times n plus 1 squared over 4. So first, so we verify that it works.
If we're like on a test, do we have to write down these like steps, the written steps?
No, it's okay. I'm just writing because I'm explaining it to you. But just make sure I understand it, of course. Okay, so for n equals 1, let me see. Sum I equals 1 until 1 of I cubed. This is 1 cubed, so that's 1. And is it equal to, if I plug in 1 here, so I have 1 squared times 1 plus 1 squared over 4. Yes, that's 4 over 4 works. Second, so assuming that this is true, so that this sum I equals 1 until n of I cubed is n squared times n plus 1 squared over 4. So we want to show, okay, 1 second, because this, we want to show so what do we want to show? That the sum I equals 1 until n plus 1 of I cubed will be what?
N plus 1 squared plus n plus 2 squared divided by 4.
So n plus 1 squared times n plus 2 squared, very good, divided by 4. That's what I want to show. Okay, put a question mark here, that's what I want to show. So let's do it. So sum I equals 1 until n of I cubed. So it's 1 cubed plus 2 cubed plus 3 cubed plus all the way, until n plus 1, sorry. N plus 1 plus n plus 1 cubed. Okay, and the term before is n cubed. And again, just like before, this is the sum until n. So I equals 1 until n of I cubed. Okay, so it's always the same process. So I'll continue on the top here. So the sum, I summarize what I wrote, I equals 1 until n plus 1 of I cubed is the sum I equals 1 until n of I cubed plus the last term, which is n plus 1 cubed. Okay, and now I'm going to assume my assumption that this is equal to n2 times n plus 1 squared over 4 plus n plus 1 cubed over, sorry, no, not over here. That's it. N plus 1 cubed. That's it, that's all. Okay, questions? Okay, so n2, n plus 1 squared plus, and here I'm going to find the common denominator, so times 4 top and bottom. Pull out an n plus 1 squared. I'm left with n2 plus 4n plus 4. And here I have over 4, and this is a perfect square. So n plus 1 squared, this is n plus 2 squared over 4, and perfect. I got what I wanted.